Hello guys, this is Dhanush Kumar from the UTD Quantitative Finance Club, and I'm also the founder and director of research of Alpha Labs, the research-based flagship program of the Quantitative Finance Club. And in this video lecture, I'm going to be deriving the Black-Scholes-Merton European option model, and I'm going to be deriving it from a very low-level standpoint, meaning I'm not going to expect a high level of mathematical knowledge from any of the users. It's going to be built ground up. So concepts such as partial differential equations, martingales, continuous time stochastic processes, so on and so forth, are not required to understand this video set. And that being said, I will explain how I'm going to lay out this video lecture series in this specific video. So again, this is going to be the first video. This is the overview. And the way this is going to be structured is going to be in two parts. So initially, we're going to have our assumptions. Now, the first video is going to be talking about the motivation. Specifically, what we do differently from other financial disciplines, and why we choose to do so. And then in 1.2, we're going to be going over how to model a financial asset. Now, the definition scope of a financial asset could be many things. It could be commodities, interest rates, so on and so forth, right? But specifically, we're going to be talking about just the underlying stocks in this specific video set. So that's going to be our definition of a financial asset. 1.3, I'll be going over something called Brownian motion. And what this is a continuous time stochastic process. And I'll go over what that really means when I get to this specific video and why it's really helpful when modeling a financial asset. And then to extend off of that, I'll be going over geometric Brownian motion. Which I'll be abbreviating as GBM. This is a very important cornerstone in financial mathematics or financial engineering, if you so will. So these initial videos are going to be used in many aspects of the field, not just European option pricing, but obviously in this video set we will be conducting a discussion and derivation regarding the Black-Scholes. And then in 1.5 we will go over what an option contract really is. And an option contract could also be thought of a financial derivative. Now, there are many financial derivatives, but in this specific case, the only two we will really be delving into are going to be calls and puts. Specifically from a European standpoint, because there is a difference between European option contracts and American option contracts, but the difference is very minute. So once we've gotten our assumptions out of the way, which are going to be these 5, which will be split amongst many videos, we can get into our derivation. So to start this off, we will be going over a Taylor expansion. Specifically to approximate a function f of x, and I'll also show how it can be used to approximate the differential of a function df of x. And I'll also explain why this is useful in our derivation. 2.2, I'm going to extend this definition a little bit to a multi-variable Taylor expansion. And specifically, we'll be focusing on functions like f of x, comma, y. So 2 independent variables. Now, once we've gotten those out of the way, we can get to a very important cornerstone in stochastic calculus, which is called Ito's lemma. And I will be deriving this using our Taylor expansions that we've discussed in the previous 2 videos. And I will specifically doing this derivation for geometric Brownian motion. Now, Ito's lemma can be used and again used to analyze many different continuous time stochastic processes, but for the regards of this video, I'm just going to be focusing on geometric Brownian motion. 2.4, we'll be going over how to construct a risk-free portfolio, why that's important. We'll also be going over risk-free rate, and going off of this, we'll also be discussing something called delta hedging, and why that's important in constructing this risk-free portfolio and, in the end, finding a fair price for a European option under Black-Scholes conditions. Once we've laid out all of those, we can finally conclude our derivation on the Black-Scholes. And this will specifically derive the Black-Scholes PDE, which stands for partial differential equation. If you don't know too much about what a PDE is, it's not too important, because in the next section we will actually be solving the Black-Scholes PDE. To get a deterministic function of European option prices, given many parameters, which will be discussed in the video set, and it won't include any differential terms. So once we've done all of that, right, once we have a formula for option prices, we can go into our last part, which I'm going to say 3, which is going to be very small, which is going to be our discussion. And this is only going to be one part, which is going to consist of a programmatic tutorial specifically using Python, though you can implement this model in, for example, Excel if you so wish to do. And we'll also be having a discussion on the use cases of the Black-Scholes the drawbacks of the Black-Scholes, as well as how to overcome those drawbacks with specific calibration methods. So this is going to be an overview of my video lecture series. And by the end of this, not only will you be able to use the Black-Scholes as just a formula, but ideally you would also be able to come up with solutions and methodologies to tweak the Black-Scholes to get better fair option prices under these conditions.